Hi, my name's Yuri and I'm a Maths PhD student at Imperial College London as well as a tutor at the Elite Prep. This is video 3 in the option pricing series, and today I'm going to be continuing with extending the risk-neutral pricing formula to the case of n-period binomial model. Previously, when we had the one-period binomial model, we had stock ST for time 0 and 1. We had R is equal to the risk-free rate. And the risk-free rate satisfied D is less than 1 plus R is less than U, where D is the down movement of the stock and U is the up movement of the stock. So this diagram looked in the following way. We also introduced the concept of a market measure last time. So the market measure is just the probability measure which represents what's really occurring in the market. So this first bit is just the market measure. We also introduced an alternative measure which allows us to compute the price of a derivative when we know its payoff at time 1. That is called the risk-neutral measure. And remember that P tilde and Q tilde from the risk-neutral measure. So risk-neutral measure, remember, it's denoted by P tilde, market measure denoted by P. Then P tilde and Q tilde took the following form. In the previous video, we said that if we have the payoff V1T and V1H for a derivative, then the price of a derivative at time 0 is just equal to the discounted expected value under the risk-neutral measure of the final payoff. Okay, so this is exactly the thing which we now want to extend. So in this lesson, we're going to consider ST, where t is equal to 0, 1, all the way through to n. We are still going to have a down movement, a risk-free rate, and an up movement. And ST we're going to refer to as one of the primary assets. The primary assets are just the stock and the money market account. There are two main foundational concepts which we need in order to extend the result above. The first concept is the concept of filtrations. And the second is of martingales. Let us start with filtrations. In the one-period binomial model, we were imagining the model as one throw of a coin, and the coin is biased. It rolls it is heads with probability P and tails with probability Q. So we denoted that as omega equals heads equals P, and probability omega equals tails equals Q. In an n-period binomial model, we instead model it as a sequence of n throws of a coin. So now, instead of omega, we have omega is equal to omega 1 to omega n, where each omega I is either heads or tails. In our case, we're going to simplify it a little bit and say that each omega I has probability P of being heads and Q of being tails. So we're just going to say probability omega I equals heads equals P, probability omega I equals tails equals Q. For more generality, you could write Pi and Qi, but it doesn't really matter. You can adapt the steps very easily to that case as well. Once you have this scenario, so our binomial model has now become a sequence of n steps, this obviously opens up more opportunity for us, right? So before, when we had the 1 period binomial model, if we imagine a real life market, and as before, the stock starts moving, it has some kind of behavior. It moves until time 0, which we're going to say is today. It had something happening before, so that's the past. And what we want to do is model the future. Well, before we had a very granular view. We had just one time step, so really we can only model what's happening at one point in the future. So either the stock goes up or the stock goes down, and we only really had time 1. Now what's happening, we are actually making it into time n, and we have slices in between each of these times. So now we can model at time 1, 2, all the way up to n. So we know what's happening with S0 at time 0. Then at time 1, it can go up or down. At time 2, there are more possibilities. So there are 4 possibilities. At time 3, let's draw another line here just to depict the situation. At time 3, it could go even further up. It could go down from the previous step, or it could behave as follows. And we'll just draw in the lines to make it clearer. And you continue in this way until you fully evolve this binomial tree. Now we are ready to introduce what a filtration is. You can imagine a filtration, F, as a sequence. In an n-period binomial model, this sequence would have n steps because we want to account for every point in time. So actually, n plus 1 steps if we're including time 0. And at each of these steps, the filtration tells us exactly the information which happens up until the time indexed by the filtration. So for example, at time 0, we have this filtration at time 0, F0. And the filtration at time 0 in essence doesn't tell us anything. It just tells us what happens at time 0, which we already know. We just know that the stock is equal to some value. If we have the filtration at time 1, that tells us exactly what happens up until time 1. So if we go and look at this graph, we know if the stock has gone once up or once down. So we know if we've thrown heads or tails. As we increase the filtration, we get more and more information because we get all the information up until the time indexed by the filtration. So if we, in this case, if we index up to time 3, if we consider F3, then we know exactly where we are out of these states. And not only that, we know exactly the path which we've taken in these states. So for example, we could have taken, the stock could do this. So we go heads, tails, heads, and we reach this value of the time 3. And that's the information which this filtration gives us. So when we condition on a filtration, it's like telling us all the information up until that time. So I'll just quickly write that down. If we have n being some value between 0 and capital N, then Fn is equal to omega 1 omega n, such that omega I is in heads or tails. So notice here now it just tells us all the throws up until time n. In more complicated models, the filtration does something more. It tells us all of the events. And actually the filtration consists of a sequence of sigma algebras. If you're familiar with this mathematics, that's something interesting to go into. For here, you don't need to understand that at all. And it's enough to think of the filtration at time n to be any possibility of the coin throws. So once we have this concept of a filtration, it's really important to compute conditional expectations of that filtration. So I think I'll first introduce an example, and then I can give the general formula for this. So for the example, we will consider the following dynamics. So imagine omega 1, i.e. the first toss of a coin happens with these probabilities. So either we throw heads with 70% probability or tails with 30%, and we continue in this way. So the throws are independent. So that means if we have 0.7 probability heads, that's the same for each of these trees. Then if we assign certain prices for S3, so say this is 110, this is 108, 106, 104, and so on, then if we want to compute the expected value of S3 given the filtration F2, this is actually a function of the state that we're at, because the filtration could have many possibilities, right? We could have this path or this path or this path. So at time 2, there's 2 to the 2, so 4 possible paths that we could take. And the filtration is a function, so the expected value given a filtration is a function of the specific path that we've taken. So here, this is actually a function of omega 1, omega 2. So I'll write that a little bit lower so I have more space. So it's a function from F2, or the specific value in F2, to R. So in particular, we want to evaluate the expected value of the stop at time 3, conditioned on the filtration up to time 2, omega 1, omega 2. And there are 4 possibilities for this, right? Because it depends on the state that we choose for omega 1, omega 2. Omega 1, omega 2 could be heads, 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 tails, tails, heads, or tails, tails. In this case, we're only going to compute it for heads, heads, because everything else is exactly the same. But in the case that omega 1, omega 2 is equal to heads, heads, we have 0.7 probability for omega 3 being heads and 0.3 probability of it being tails. So we just have 0.7 times 110 plus 0.3 times 108. And we will continue in the same way for all of the other ones. If instead we were trying to compute the expectation of S3 conditioned on the filtration at time 1, then this is just a function of omega 1, because the filtration at time 1 only tells us something about omega 1. And then omega 1 only has 2 possibilities, either heads or tails. So we just have to account for omega 1 equals heads, omega 1 equals tails. And after that, we would go through computing the expectation across all of these values. So we would calculate 0.6 times 0.7 times 110 plus 0.6 times 0.3 times 108, and sum all of these. And we would continue in that way. So you can complete that on your own. The general formula, so imagine we have 0 is less than little n is less than or equal to n. Then the expected value of Sn conditioned on the filtration at time little n, evaluated at omega 1 to omega n, is just equal to the sum. And for now, we're going to, again, make this assumption that all the probabilities match up. So probability of throwing heads is always P, probability of throwing tails is always Q. That just makes notation easier, but you can rewrite this in another way too. That would be P to the power of number of heads in omega n plus 1 to omega n, q to the power of the number of tails in omega n plus 1 to omega n. And finally, you just evaluate Sn at the path, which is omega 1 dictated by these, so omega 1 to little n. And then we append the path omega n plus 1 to omega n. The sum is over all possible paths if we start at the node which we condition on. Okay, so there's a really important theorem for these conditional probabilities, and I'll introduce it now. In essence, this theorem tells us that a conditional expectation behaves in the same way as an expectation. By that I mean, first, it is linear. So if we consider two random variables, x and y, then if we condition on the filtration at time n, then we could just expand it as the sum of the conditional expectations of each of these random variables. The second part of this theorem is measurability. So again, if you have two random variables, x and y, acting on the probability space of these coin throws, then the expected value of x, y conditioned on the filtration at time n is equal to x times the expected value of y given the filtration at n, if x is known by the filtration at time n. So if n in essence tells us everything we need to know about the filtration. So an example here is if we were computing expected value of S1 times S3 conditioned on F2, then S1 we actually know by this time because we know the path that we've taken, so we know the price that S1 had. So in that case, we would just have this is equal to S1 times expectation of S3 given F2. So that's just one example. The next part of this theorem is independence. So whenever we have a random variable, if it does not depend on any of the time points up to time n, then the expectation of that random variable given the filtration is just equal to the unconditional expectation of that random variable. Finally, another really important part is the Tower rule. The Tower rule allows us to iterate conditional expectations, and the result is that the conditional expectation with the earliest time is the final conditional expectation. So if we start with n, which is earlier than m, then the conditional expectation conditioned on the filtration up to time n of the conditional expectation up to time n is just equal to the conditional expectation up until the filtration time n. So that's everything we need about filtrations and conditional expectations in order to introduce the concept of a martingale. Put simply, a martingale is just a way for us to rigorously model a fair game. So if you're playing a game, if that game has n steps and you're at step 2, then at step 2, you would expect that the game has value the same as what you're currently at. So you're not going to win any more or lose any money by playing that game, because then that would make it a quote-unquote fair game. The rigorous definition for this is as following. If we have a sequence of random variables, x0, x1, up until xn, if xi is known by fi, we're going to say if xi is measurable with respect to fi, then the sequence xi from I equals 0 to n is called an adapted process to the filtration f. So we should have fixed the filtration first and then define this sequence of random variables such that at each time, the random variable indexed by that time is measurable with respect to the filtration at that time. So then we say that an adapted process is a martingale whenever the conditional expectation of xn plus 1, conditioned on the filtration at the previous time step fn, is just equal to the random variable at the previous time step. And here it should be intuitively clear why this makes sense as a concept of a fair game. So if you get to a time n, then the expected value of the future game is worth no more or less than the current value. So we won't win any money or lose any money by playing it. So it's fair. Once we have the definition of martingale, we can then define a risk-neutral probability measure in the case of this general model. Remember that in the one-period model, we defined the risk-neutral probability measure as the one which allows us to have the same return for all of the primary assets, so the stock or the money market account. In this case, we need this definition of martingale. So we say that the risk-neutral measure is the one where every primary asset after discounting is a martingale. In our case, we only have one stock and the money market. The money market, when discounted, is always just one value. So because it's a constant, this expectation is always just equal to itself. So let's be more thorough. So we're going to say we have B0, then we have B1 equals 1 plus R B0, and then Bn is equal to 1 plus R to the power of n B0, because that's just us earning n steps of interest rate on B0. Then we're gonna, so I'm gonna introduce this definition of a risk-neutral probability measure. So I just said that. So going back to the money market example, this is trivially a martingale because Bn over 1 plus R to the n is just equal to 1 plus R to the n B0 over 1 plus R to the n, and that's equal to B0. So that means that expected value of Bn plus 1 over 1 plus R to n plus 1, conditioned on Fn, is equal to expected value of B0 conditioned on Fn. And B0 is a constant, so it's measurable with respect to Bn. So that's just equal to B0. And that is also equal to Bn over 1 plus R to the n. So the money market is trivially a martingale. So then we just need to deal with the stock. So we need the probability measure. So this is true actually under any probability measure. Then for the stock, we need the following. We need Sn over 1 plus R to the n being equal to the expectation under the risk-neutral measure of Sn plus 1 over 1 plus R to the n plus 1 conditioned on Fn. And we can use this to derive the risk-neutral probability measure. That's just done by moving forward step by step and calculating the P at each step. Now, once we have the risk-neutral probability measure, we can actually prove the fundamental theorem of asset pricing. I.e., we can prove one direction right here, which says that if we have a risk-neutral probability measure, then there doesn't exist arbitrage in the market. So the theorem which I'm going to say is recall that an arbitrage is just the existence of a trading strategy, which you can start off with zero capital and trade in such a way that with probability greater than zero, you have positive value of your portfolio at final time, and you have a zero probability of having a negative value of your portfolio. We will consider a general trading strategy where then our n+1 time, so we're going to say our trading strategy is x n+1. That's the value of our portfolio at time n+1. That's equal to delta n of the stock at n+1, because the stock at time n would have been Sn. At time n, we had delta n of that stock. So at time n+1, we would have that the stock goes up to the price Sn+1, but we still have delta n of that stock because we can only update our trading strategy at the time and not between the two times. So we would have to wait for the stock to reach n+1 until we can change delta n to delta n+1. So this is the effect of the stock. And on top of that, we also get the interest rate from everything else which we have in the bank account. And what we have in the bank account would just be everything not in the stock at time n. So that would just be xn minus delta n Sn. Now, I want to show that the trading strategy is actually a martingale after discounting. So I'm going to then compute under the risk neutral measure. Then I just use linearity of expectation, and this should have been a conditional expectation. Then in both cases, I use measurability. The only thing here which isn't measurable is Sn+1. So we just have that's equal to delta n, an expected value under the risk neutral measure of Sn+1, which is a primary asset, plus everything inside the other part is measurable with respect to the filtration at time n. So that is just xn minus delta n Sn over 1 plus r to the n. And we also use the fact that all primary assets are martingales. So this is just equal to delta n Sn over 1 plus r to the n plus xn minus delta n Sn over 1 plus r to the n, which is just equal to xn over 1 plus r to the n. So that means that the trading strategy is a martingale. Once we know that the trading strategy is a martingale, we can apply the Tower property to iteratively compute the price of a trading strategy at time 0. x0 is just equal to the expected value of x1 over 1 plus r of f conditioned on f1. That's equal to expected value of, because by martingale property, we have x1 over 1 plus r is just equal to the expected value of x2 over 1 plus r squared conditioned on f2. And we keep doing that until we have that's equal to expected value of xn over 1 plus r to the n conditioned on fn minus 1. So all in all, this is by the Tower property equals to expected value of xn over 1 plus r to the n conditioned on f0, and that's just equal to the expected value of xn without divided by 1 plus r to the n. To conclude the proof that there's no arbitrage, we notice the following. We assume by contradiction that there is an arbitrage, then and we assume this is a trading strategy which creates that arbitrage. Then we know that probability xn is greater than 0, probability that xn is greater than or equal to 0 equals 1. And by definition of the risk-neutral measure, we know that the probability of xn is greater than 0. Sorry, these should have been the market measure, and then we have the probability under the risk-neutral measure is greater than 0, is greater than 0, and the probability that xn is greater than or equal to 0 equals 1. And then that means that the expected value under the risk-neutral measure of xn over 1 plus r to the n must be strictly greater than 0. And that means x0 was equal to that expectation is strictly greater than 0. But if x0, so by existence of arbitrage, x0 was equal to 0, so we actually have a contradiction. In other words, we cannot start with 0 capital and create money from nothing. So finally, we return to the risk-neutral pricing formula, and the theorem becomes that given the payoff of some replicable derivative, which takes values vn, omega 1, omega n, then the price of v at time n less than or equal to n is given by the discounted expected value under the risk-neutral measure. So Vn over 1 plus r to the n is just equal to the expected value of Vn over 1 plus r to the n conditioned on the filtration at time little n. This can be seen in the following way. So say we've assumed that the derivative is replicable. So that means there's a trading strategy such that xn equals vn. Every trading strategy is a martingale. We've shown that before. So we know that x little n over 1 plus r to the n is equal to the expected value of x big N over 1 plus r conditioned on fn is equal to expected value of Vn over 1 plus r to the n given fn. And finally, by definition, xn, x little n, has to be equal to Vn, because otherwise we would have two ways of creating different payoffs, and that means we would be able to create an arbitrage in the markets. That is everything. I hope you enjoyed that video, and thank you for watching.